Yes, class. Good evening.
Good evening, teacher.
So, Atif, Fatima, Hamza, Hiba, Huzaifa, Krishna, Sarah. Okay. See, class, we had started with total internal reflection. So, and we had also completed apparent depth in the last class. So, total internal reflection was what? We had discussed that the phenomena and the steps that occurred in total internal reflection. See, when the light travels from denser to the rarer medium, when it travels from the denser to the rarer medium, then angle of refraction is there, angle of incidence is there. Now, as you keep on increasing the angle of incidence, angle of refraction also increases. Then you increase again the angle of incidence and you get such a value of angle of incidence that for which the angle of refraction becomes equal to 90 degree. That is known as, this angle of incidence is known as critical angle. Right? This angle of incidence, this is known as critical angle. Now, if we exceed this further, this angle of incidence, if this is exceeded further, then instead of the ray getting refracted, now the ray gets reflected within the denser medium. Instead of getting refracted in the rarer medium, the ray gets reflected in the denser medium. So this phenomena is known as total internal reflection. Total internal reflection comes usually for a long answer question, not a very long answer question, 3 marks it comes, where you have to write down the definition, you have to draw this diagram, you have to explain this diagram, as well as you have to mention the applications of TIR. So regarding the applications of TIR, that we'll do, we have not discussed it yet, that we'll do in today's class. But before that, all the things that we have already covered are all these parts. All right. Okay, so we had done angle of, yes, critical angles, numericals are tougher. Comparatively, one numerical we have already done, which is a good numerical. One more leads to it. So there is no such formula for critical angle. It simply gets the application of the Snell's law. So Snell's law, how do we use it? Refractive index of one medium multiplied by sine of angle of that, which is equal to refractive index of the other medium multiplied by sine of angle of that. So this was a very easy question. This was a good question that we had discussed. One more question let's discuss. So as I've already told you people, critical angles, numericals are sometimes difficult. So have a good practice of it. See, let's discuss this question, then you can note down the question as well as the solution together. A pipe is given to you. Fine, this is a pipe, and see, this is just a pipe. This is showing the outer part of the pipe, and this is the inner part of the pipe. Now, this figure shows a cross section of pipe made up of glass fiber of refractive index 1.68. See, basically this question says what? There's a pipe, hollow pipe is there, so inner and outer radius will be there. Outer part of the pipe has the refractive index of 1.44, whereas 1.68 is the refractive index of the inner part, the denser part. Basically, this is the rarer part, this is the denser part. Then see, a ray of light is incident. This is your ray of light. Rest of the part is air. You're not concerned with this part. This is air. From where the light ray has entered, simple refraction has occurred, but as it struck this surface, the incident angle became greater than the critical angle. And when it became the greater than critical angle, total internal refraction occurred. So see, if TIR is to be occurred, then what is the value of angle of this angle of incidence? Not this critical angle. Critical angle's calculation is very easy. We have to find out this angle of incidence. Fine. So before we find out anything, at least let us find out the value of critical angle, so that we'll be able to get an idea that how much by which value is the angle of incidence greater. Because let's say angle of incidence is 30 degree, so we can critical angle is, for example, 30 degree, so we can figure out this fact that angle of incidence will be greater than 30 degree. Rest of the things we'll be able to calculate later on. So that was what was written in the question. Range of angle means whether it's greater than the critical angle, a certain range for it, greater than this value, lesser than this value. So a specific range it is asking us to calculate. All right. So see, let us first calculate the critical angle. Critical angle, as I've told you. See, first calculate NDR, that is ND divided by NR. Denser is given to us, the bottom one, that was 1.68, and rarer was 1.44. Sin IC, this is a lengthy question and not a very lengthy question, but yes, one of the good questions for critical angle. So pay attention to this. We'll be doing it in parts, so whichever part you'll not be able to understand, let me know. So critical angle we have already discussed in the last class. This is 1 by NDR. If critical angle is 1 by NDR, so I can just reverse this. This is 1.44 divided by 1.68. I have obtained the value of sin IC. See class, when you will solve this, you will get it approximately 0.86. You can cross check. Once you divide it, see whether it is 0.86 or is it something else. So sin IC is 0.86. Now this is very useful for us. Now one thing for sure, if total internal reflection has to occur, and it is occurring, we are sure about this fact that yes, total internal reflection is occurring. We are not sure about the angle that is present. So for total internal reflection to occur, we can simply say for TIR, angle of incidence is greater than critical angle. Fine. So it means sin of I is greater than or equal to, also you can say. For this question, we can take the minimum value. And what can be the minimum value? Slightly more than 0.86. So slightly more than 0.86 means almost equal to 0.86. Angle of incidence is greater than critical angle. But for our numerical purpose, we can equate because we do not have any other data. So this is greater than sin IC. Fine. Sin IC part is clear. So it means sin I will be what? Sin I will be greater than 0.86 because sin IC was 0.86. Clear till here? First tell me. Clear
Yes.
till here? Okay, good. Only clear to Fatima or to others as well?
Clear, ma'am.
Okay. Anybody has any doubt? Let me know. Because it can happen. Critical angles questions are little lengthy. See, if this is angle of refraction, this is angle of critical angle basically. Critical angle, which, or you can say angle greater, not critical angle, this is the angle that is greater than critical angle. and this is 90 degree, this small triangle here. So it means all the sum of these three angles is 180 degree. If said I plus this R, see this angle I plus R plus 90 degree will be equal to 180 degree using triangle angle, this triangle angle sum property of triangle. Angle of incidence plus angle of refraction will give us 90 degree. From here we can get the value of this, that is 90 minus R. Now why are we doing this? Because we need cos in our, we need the value of sin R. See, what are we trying to calculate right now? If we have this, see class, if we apply Snell's law, so refractive index of the medium, see, let me tell you what are we actually trying to calculate. We need this angle of incidence, right? This medium is air. So refractive index of air, what did I tell you in the last class? Take refractive index of air as 1. Okay, it's 1. If nothing is given, it's 1 only. So 1 refractive index of air multiplied by sin I. This will be equal to, now the refractive index of this material, 1.68 into sin R. Because if you apply Snell's law over this point, now if I know the value of sin R, so nothing is left in the question, sin I will be calculated. If I know this value, then sin I will be calculated, angle of incidence will be given. That's the only problem. We do not have this angle of refraction. So using the help of this, with the help of this critical angle, what are we trying to find out? We are trying to find out sin R. If we have sin R, one-liner answer was this. If somehow you can calculate sin R, not sin R, just the angle of refraction in any manner, one line your answer will come. Understood? That's what we are trying to calculate over here. So angle of incidence was required, that's why. And here this is I is equal to 90 minus R. Now substitute it. This is angle of incidence. This is not actually angle of incidence. You can write it as I prime. This is that angle which is greater than critical angle. So that is not angle of incidence. You can write it as I prime. So that at least it gets differentiated with that I we are doing. So sin 90 minus R I can write. It was sin I greater than or equal to 0.86. So instead of sin I can write I as what? 90 minus R. Now see, this will give me cos R, 90 minus theta greater than or equal to 6. So cos R, now I can get the value of sin R. How? See, sin R is under root 1 minus cos square R. Using the identity sin square theta plus cos square theta is equal to 1. If I use this identity class, sin square R plus cos square R is equal to 1. From here, I can get the value of sin R. And here cos R was unknown. That's why I had performed this calculation so that I can get the value of cos R. Now, if I have this value, so sin R will be under root 1 minus 0.86 whole square. This will be 0.26, somewhat 0.26. This will be equal to. So now we have sin R. So sin R is greater than or almost equal to 0.26. This is the minimum value. It will be greater. This will be greater than that only. So sin R is given. Now see, sin R you have, sin I you have. If you have I and R with you, you can just put it in that formula. If you apply Snell's law at the very first step. So what will you get? If you apply Snell's law, you will get refractive index of air multiplied by sine of angle equal to refractive index of the pipe that is given multiplied by sine R. Now we have value of sine R. Angle of incidence can be calculated. So sine I will be 1.68 into 0.26. So sine I will be 1.68 into 0.26. This will be 0.436. Please cross check once. So sine I will be 0.436. It should be around this. So I will be what? Sine inverse. Not exactly make it equal. You can write it as greater than or equal to sine inverse 0.436. This becomes your answer. So Snell's law's application. See, Snell's law is a very easy formula if you see. Sin I by sin r is equal to n2 by n1. But its applications are difficult. First, tell me, all of you, if have you understood any part or not? Understood or not? Atif, Fatima, Hamza.
Yes, ma'am.
Clear? Any difficulty or any doubts in this?
No, teacher.
Ma'am, can you explain it once more?
Yes. See, in this question, incident ray came, it got refracted first, and now the angle of incidence became greater than critical angle, so it got totally internally reflected. Now we are supposed to find out this angle of incidence. You can mark this as I prime to differentiate. I had taken both of these as I, so it can be confusing. Please correct wherever it is I prime. We have to find out this. So if you, this step you have understood, how to write this step?
Yes, ma'am.
Okay, this is, so see, if we are just somehow trying to find out sin r, this is our purpose. If we get sin r, I can be easily calculated. So to get r, we have this triangle beneficial for us. Angle of critical angle can easily be calculated using NR and ND, how we have discussed it in the last class. So critical angle will be 0.86 when you will solve this. This is clear how critical angle has been obtained?
Yes, ma'am.
Okay. See, for total internal reflection to occur, angle of incidence has to be greater than critical angle. This is that angle of incidence, the other one, which is greater than critical angle. So this is written. If we find out that angle, then angle of refraction can easily be calculated from here. Because right now our purpose is how to find out refractive angle. If angle of refraction is given using Snell's law, easily our answer would be given. Now see, from here we have obtained that I prime is 90 minus r using that triangle. If I prime is 90 minus r, I have kept it in sine theta. So sine 90 minus r became greater than or equal to 0.86. Why are we constantly using greater or equal to? Because angle of incidence is greater than critical angle. And to take a minimum value, because how will you equate it otherwise? How will you solve the question? So we are putting an equal to sign as well. That least to least, this can be the value possible. Otherwise, it is not possible to have the value for it. Fine. So this is sine 90 minus r. From here, I have got cos r. Why did we do this step? Because sine r is under root 1 minus cos square r. So I have to have cos square r with me. So using these two steps, I'll get cos square r. From this, I have obtained the value of sine r and I've kept it in the main formula. Got it?
Yes, ma'am.
Okay. So all of you do one thing, note it down. If any part you have still not understood, let me know. I'll repeat that part. And mark this question again as important. All these questions based on total internal, not total internal reference, especially which involves your critical angle. So critical angles, Snell's law are used in this way only. See, that's the condition for total internal reflection to occur. If total internal reflection is occurring, it means this angle, let's say this angle is I dash. So this I dash must be greater than the critical angle. That's why total internal reflection has occurred. So
No,
that's
but
why
we wrote greater than or and equal, greater than or equal to, right? So why
Yes.
equal to? Matlab,
Equal
how?
to ECC, equal to in this way. For example, let's say critical angle is 30 degree. All right. It means your I prime must be greater than 30 degree. Minimum value of I prime can be what? It can be 30.1 degree.
Yeah.
This is also greater. So since for our calculations, we cannot take the approximation with this sign, we cannot equate it, and we do not have other data to find out the value of angle of refraction. So that's why if it is 30.1, so we are equating it to this extent that yes, almost it is equal to 30 degree, but yes, we know that it is greater than 30 degree. So that's why if it minimum value that is possible is 30.1, from here, no, it will keep on increasing. Or not even 30.1, this is also greater value that I've taken, 30.001, something like this. So that's why we have put in an equal to sign to equate that minimum it can be. It is actually not equal, but the magnitude can be taken as equal for our calculations. Understood?
Yes, teacher. Thank you.
Written?
Yes, teacher.
All right. Now, applications of TIR. This you can refer to the book also for writing it in detail. I'll explain you certain important applications of TIR which are present. See, this is a kind of optical illusion. Mirage formation is an optical illusion. Let's take an example. Supposedly, some object is there on a road. Let's say a tree is present on the road. See, atmospheric layers are also present. The layers of atmosphere are present. So these have different refractive index. All these atmospheric layers have different values of refractive indices. It means refraction can easily occur from here. So as soon as the incident ray strikes from the object, this is the incident ray, as this is our object now. So incident ray strikes, it gets here, it gets refracted. Again, it gets refracted. Like this, it keeps on getting refracted. Then again, what happens at a certain level, if the angle of incidence exceeds which angle? Critical angle. If somehow this angle is exceeded, then which phenomena will occur? If this angle of incidence is exceeded, what is the name of the phenomena that occurs?
Internal reflection.
Total internal reflection. Exactly. So total, according to total internal reflection, this light ray which had to be refracted over here, now this is getting reflected back. And that's why here you will be able to see the image on the road. Road is not a plain, smooth, shiny surface, and obtaining image here was not possible. So that's why, because of the different refractive indices that are present, rays go from denser to rarer. Fine, all the rays go from denser to rarer. And one more thing, see, as the refractive index increases, the temperature decreases. So what happens? Some of the optical illusions, you can take this example. The sky is present above, bluish color is there. So what happens? The rays, incident rays come from the sky. And when these come from the sky, all these rays of light, what happened to it? Gets refracted by the atmosphere. As the angle of incidence, this angle exceeds the critical angle. So what happens? It becomes greater than critical angle, and it's already from denser to rarer. Total internal reflection occurs. So you are able to see sky's image reflection on a dry road, usually on a sunny day, and it appears as if water is present on the road. So it's an optical illusion. When you'll go towards the water, where you are able to observe the image of the water, you will see the road is completely dry. That is just because of mirage formation. So this process is known as mirage. This is one of the applications of TIR. Regarding the details of it, how to mention it, how to write it, that you can refer from the book. But do include these whenever you include your answers for TIR. Second is brilliance of diamond. Brilliance of diamond means the shining of diamond. Diamonds keep on shining. See, this is a diamond. What happens? Light gets incident. At this surface, TIR occurs. At this surface, TIR occurs. Similarly, at all the surfaces, total internal reflection occurs. Here also TIR occurs. Here also again TIR. This way the light keeps on moving within this. Once the light gets trapped, here what happens? It becomes difficult for the ray of light to escape out from the diamond. So that's why once light ray has entered in a diamond, when we move or shift the diamond a little, the ray of light keeps on getting totally internally reflected. So basically light traps. Also one more thing, why is this possible and why is the ray of light not able to get out? Because angle of this critical angle is very small. So if the threshold is only small, the critical angle is only small, so angle of incidence can easily exceed it. And once it is exceeded, you will get total internal reflection occurring. So one of the reasons why we have brilliance of diamond is small critical angle. Small value of critical angle. So since the threshold is only so small and also it has a high value of refractive index, one more thing, you can even remember the value of critical angle. It is approximately 23 degrees. This is approximately 23 degrees. The critical angles were not 23, 27. Is 27 degree, not 23. This is 27 degree. So if any angle is greater than 27 degree is not a very huge number. Usually critical angle values for all the different substances are huge and greater than these. One more thing, prism. Prism, we have a separate topic as well. We'll be dealing with prism also. But right now, see, in prism also you can remember. It helps to reflect the light. This phenomenon of TIR occurs in prism, and this phenomenon of TIR helps to reflect the object. For example, let's take this. This is a right-angled prism. Here, this is right angle. So definitely this angle will be 45. This angle will be 45. Now I take an object over here. What will happen to the light rays? It gets strike. Then at this surface, total internal reflection occurs. And this is the path of the light ray that occurs. It goes, then it gets totally internally reflected. See class, if this was the object AB, now here I am obtaining the image A dash, B dash. So see, image was like this. Now image is like this. It means it has been reflected. So it helps in reflecting ray by 90 degrees. So like this, one example is this. Let's take one more example. Though we will discuss prism, so do not worry about the prism, but yes, total internal reflection is being discussed, so we'll mention it over here. Now I am keeping this right angled prism. This is 90 degree, this is 45, 45. This part was there, no? Same part I am taking. Now this is acting as the surface area for reflection to occur. So this is the object A, B. If I keep the prism in this direction, light rays will fall, light rays will fall. It gets totally internally reflected. This gets totally internally reflected. Again, this is a surface, it will get totally internally reflected. This will also get totally internally reflected. I have not drawn it properly. If you draw it with the help of scales, so you'll get a proper diagram. And this is also not 90 degree. This also you can make it correctly. So now see, this is B dash, A dash, B dash. So it means reflecting rays by 180 degree. Reflecting rays by 180 degrees. So entire ray has been completely inverted. So like this, you can use prism and total internal reflection phenomena can occur and images can be reflected. So it helps in reflection of images. It's used in prism. That's how much you can remember. And also for prism, critical angle is 42 degrees. This we'll do in prism as well. Critical angle is 42 degrees and refractive index will be 1.5 only. Refractive index of glass we'll be considering. Last is the example that we did, the question we have just completed. The question you all wrote, no? Optical fibers it is used. Optical fibers, are you aware of? Optical fibers are normal. These fibers that we see, these are usually used in computer devices. The way you must have seen optical mouses are present. They have a scroller with a light below the base of the mouse. So they have these optical fibers with. Actually what happens, this is the wire. light is incident, it gets reflected, totally internally reflected. It gets totally internally reflected, it gets totally internally reflected, like this. This is the denser, this is the rarer. Same question that you have done. That's why you were able to solve and get the answer for that question. Reason, because optical fibers have the application of total internal reflection. All right, so these are some examples that you can do. Note these down. Any queries from total internal reflection, you can ask me. Then we'll start with spherically refracting surfaces. Now, spherically refracting surfaces and lens, optical instruments, and this prism part is left. And on Thursday, we have a test, as I've already announced in the last class, from just a topic reflection. A short test will be conducted. Okay, so this completes your total internal reflection. Now let's start with spherically refracting surfaces. This derivation of this part is very lengthy derivations are there. Lens is comparatively shorter as compared to this. The derivation only will consume the entire class. Derivation can be asked. Questions for this refracting, usually numericals are asked from this, but question can be asked. It can be given. See, for spherically refracting surface, what's the difference between a spherically refracting surface and a mirror? Just see, this is a hollow sphere that we have glass. Center of curvature is here. This is the radius of curvature. Center of curvature, radius of curvature, all these terms you were already aware of. Now, if you put a cut onto it, this is a glass sphere with you. If you put a cut onto it, this we had discussed, the same steps we had discussed when we were discussing reflection. See, one part that you will obtain will be this. And if you cut it from here, the other part that you will be obtaining will be from here. Now, if I polish this surface, I'll get a concave mirror. And if I do not polish this surface, then see, reflection cannot occur now. This becomes glass, this becomes air. So glass air interface, now refraction will occur. If you polish this surface, then this becomes glass only and reflection keeps on occurring. Understood? This is the same step as we had started when we were discussing mirrors. In case of mirror, if you polish this surface, you obtain a mirror. And that time reflection occurs. Now, since this is glass, this is air. This is rarer, this is denser. So refraction will occur. So there will be center of curvature, there will be radius of curvature, there will be a pole, and this becomes your convex surface. Because this is glass now, refraction is occurring from this. This is the incident part, so that's why convex. Similarly, I'm not polishing either of these surfaces. No surface requires any polish. So this is denser, this is rarer, this is center of curvature, this is radius of curvature, pole, and this becomes a concave surface. So understood the difference. This is the same as we had started with reflection. The difference that arose over here was the fact that we had painted this. We had polished one of the surfaces. See, how are we going to study refraction? Basically, we are going to study relation to unite object distance, image distance, radius of curvature, and refractive indices of both the denser and the rarer. A relation we are doing, and this relation is the only formula that will be used. Proper sign convention and everything will be used. That we'll see. But formula is a little lengthy. See how we are going to study it. One is from rarer to denser, which involves both your convex surface as well as your concave surface. And the other involves your denser to rarer. Both convex and concave. Now, one thing class, here you have the type of images that you will obtain will be real and virtual image. Real or virtual images, any of it. Real or virtual images, not and or real or virtual images. Note down this part, then we'll start with the first one, rarer to denser. So quickly note it down, we'll start with the first derivation. See class, now we are doing refraction from rarer to denser surface. It means this is N1, this is N2. So this is N1 is your rarer surface and N2 is the denser surface. Now this is an object. Rays of light are incident. See, again, I'm telling you the derivation is lengthy. So please pay attention, and wherever you're not understood, stop me and interrupt in between. Now at this surface, this is the normal. Let's say this point is M. Now at this point, refraction occurs. This is image. Let's say this angle is alpha. This angle with the principal axis is made as beta. And this angle that the normal makes with the principal axis is gamma. Why are we considering all these? Because with the help of angles and triangles only we'll be able to do the derivation. That's why we are specifying these angles. These angles as such have no meanings. They have no special or a specific physical significance. This we have taken for our derivation purpose. Tan x we will take, so it's better we take a tan alpha. This becomes angle of incidence. And this becomes angle of refraction. Refraction will be confusing with gamma. No, let me change the font of our. This is angle of refraction. This is gamma. One more thing, one more construction. This will be required. A perpendicular I'm dropping, which is N. This I'm using because we have to actually connect M and this aperture P. But since we know this is a curved surface, so all these curved surfaces will be having, you cannot consider MPO as a triangle, no, for the derivations, because this is a curved surface. So we are taking a very close point to P, that is N. So whatever answer you will get for ON, that will be equal to OP only. That I'll tell you later on. So this is object from the pole. This is known as object distance. This is radius of curvature. Sorry, I didn't mark this. So this becomes radius of curvature. And this complete is image distance. Fine. Understood the diagram, the figure? You have understood, all of you? Because all those who are listening will be able to understand. Otherwise, afterwards, if you see, then it will be confusing.
Ma'am, is MN perpendicular?
Yes, MN is a perpendicular. To make it perpendicular, and because there was no presence of perpendicular, and without perpendicular, we cannot apply all the trigonometric functions. That's why MN is a hypothetical perpendicular that I have drawn that has no relevance in your ray optics, no meaning in ray optics. It's just a perpendicular that I have drawn. And this PN distance is very, very small because we cannot use this triangle, no, OPM, because see, P is a curved surface. It will not give you any part. So just to elaborate and elongate it, we have just straightened it up by dropping a perpendicular. Okay, Krishna?
Yes, ma'am.
Okay. See, if you apply Snell's law at this point, if you apply Snell's law, N1 is the refractive index multiplied by sine I. This is equal to, what did I tell you? Again, the refractive index of the other medium multiplied by angle of refraction. That's how we have been using. Fine. Now see, if the small aperture is there, we are considering this for a small aperture. Two approximations will be used here. One is small angle approximation will be used. Other approximation is this. P and N are very close to each other. So if a small angle approximation we are considering, it means sine I will almost be equal to angle of incidence. Sine R will almost be equal to R. Understood? Because see, if small angle means angle less than 15 degree. So if an angle has a value 7 degree, so if you check log table and properly see the value of sine 7, no, that will be approximately around 7 only because it is so small. So instead of writing sine 7 degree, or you write 7, both are same. Similarly, you have sine I approximately equal to I, sine R approximately equal to R. So now this equation, to simplify, we can write this equation as N1 into I, N2 into R. Now, angle of incidence and angle of refraction we have to find out from this triangle. If you remember exterior angle property, look at this triangle OMC, this triangle. Exterior angle property, all of you must have done it in your 10th standard. Exterior angle property simply says that exterior angle of a triangle is the sum of the angles of the opposite side. It means if this is the exterior angle, see this is the triangle OMC, in triangle OMC, these are the angles and this is outside. So I will be equal to alpha plus gamma. Yeah. Similarly, if you look at this triangle IMC, in triangle IMC, see this gamma is now the exterior angle. So how can I write gamma? Look at the figure, try all of you. One I have explained, other answer. Look at this triangle IMC.
R plus beta.
R plus beta. Good, Krishna. So gamma will be equal to R. Let me write it in this way. R plus beta. So from here, R will be equal to what? Gamma minus beta. So let's keep these values of I here and R here. These are the values of I and R that has been obtained. So this becomes I n1 into I. So I can be written as alpha plus gamma equal to n2. Sin R has been written as R, and R is gamma minus beta. Now alpha, gamma, beta, gamma has to be obtained. See, we are using a small angle approximation. This is by small aperture is there. So that's why we are using small angle approximation. So if small angle approximation is valid, then tan theta will also be equal to theta. So tan alpha, see if you look at this triangle OMN, from here you can obtain, that's why just for this step we had to draw this perpendicular MN. Tan alpha will become MN by ON. Fine. Tan beta will become MN by NI. So tan alpha is there, tan beta is there, and tan gamma. Tan gamma will become Mn by Nc. Clear? See, for tan alpha, triangle OMN, Mn by On. Clear? Then for tan beta, this is triangle IMN. This is equal to Mn by Ni. Perpendicular by base you have for tan theta. And for gamma, you can use this triangle Mn by Nc, MNC triangle. Clear? So it means you can write tan alpha almost equal to alpha as Mn by OMN, so NO. ON. Tan beta, which is almost equal to beta, you can write it as Mn by Ni. This was obtained from the triangle OMN, and this is obtained from the triangle MNI. One last, that is gamma. Gamma is obtained from that narrow triangle CMN. So tan gamma is approximately equal to gamma, which is equal to Mn by Mn. So Cn divided by Nc. This is by the triangle MNC. Now you have values of alpha, beta, gamma. Put it in this equation. So you will obtain N1. Now it was alpha first, so alpha plus beta. So this becomes Mn by On plus Mn by Nc. Equal to N2 was gamma minus beta. Alpha plus gamma is this only, Mn by Nc. Minus beta was Mn by Ni. Now the major part has been done in the derivation. Now we just have to put in everything here and rearrange. See, Mn gets cancelled. and C class. Now N has no significance. What is ON? What is NC? Nothing. It means P and N are so close to each other that now you can replace wherever you have written N by P. So ON can be written as OP, and OP is what? Object distance. Ni can be written as Pi. Pi is what? Image distance. Cn can be written as Cp. Cp is radius of curvature. Understood? So instead of On, I'll write now Op. Instead of Ni, I'll write it as Pi. And instead of Cn, I'll write it as Cp. Wherever it is required, just replace it with the same. So ON becomes approximately equal to OP. This is a negative of the object distance. NC, which is almost equal to PC now, this is equal to refractive index, it will be positive. And NI will approximately equal to PI, which is plus V, image distance. Now keep it in the main formula. Instead of ON, replace all these terms wherever you've used. So that becomes N1 by 1 by minus U plus 1 by R is equal to N2 1 by R minus 1 by V. Now we just have to assemble. This is the answer. This is the formula. Let's make it a little simplified, multiplied. N1 by minus U by N1 by R is equal to N2 by R minus N2 by V. Very lengthy. This derivation is very lengthy. Let's interchange all the terms having radius of curvature together and U and V together. So N1 by minus U plus N2 by V is equal to N2 by R minus N1 by R. You can keep it here also, or you can take the common N2 minus N1 by R. This is the final answer. And you have to use a proper sign convention. Only it's the case of optical instruments where sign convention is not required. That we do when we do optical instruments. Rest of the case, you have to do it. See, definitely this is a very lengthy one. So do this, and parts by part, I'll ask you if you have any doubts from any part. So write it down, keep on, because see, now the other part is what? From denser to rarer. That we'll do very fast. Very fast, same derivation, almost same derivation is there. A lengthy and a similar derivation is there. So what I'm going to do right now, understand this first. If you will understand this, rest of the almost the whole class will be over for today. So what you can do, write it down in parts. I'll keep on asking you whether you have any doubt. So from that part, if you have any doubt, you can ask me. Otherwise, you can note it down. If you have any doubts from the above part, that is the figure, the construction, and how we have obtained this equation. Because we just have to substitute everything in this equation, rest of the derivation is just elaboration of it.
Ma'am, can you scroll a bit up?
See class, now this is from rarer to denser. This is the glass part. I have just extended this so that you understand that this is the convex part. Why are we getting it? This is now the convex part. This is the glass part. Otherwise, you can even ignore these lines. Same things will be given. Now the normal will be here. This will be the normal. And your M point will be this. This will be your M point. Again, you will drop a perpendicular MN over here. This is the center of curvature. Normal passes through the center of curvature. And this gets refracted, image is obtained. Same, alpha is there, beta is there, gamma is from here. And angle of incidence will be this, because it's the angle between incident ray and the normal. And angle of refraction will be this. This will be angle of refraction. This is the point M. So it's just that since the surface is now has been changed, denser and rarer has been changed. So that's why, because of the convex surface, we are getting this. Otherwise, this was just shifted over here. The rest of the things will be the same. C class. Now, if you apply exterior angle property in this triangle OMC, here if you apply, gamma is outside. So gamma is equal to I plus alpha. So from here, you can say I is equal to gamma minus alpha. And in this triangle MCI, if you look at this triangle in triangle MCI, I is exterior, so gamma plus beta. This is I. No, in this triangle, I will not be exterior. R will be exterior. R will be exterior. I is not outside this line. This is not complete. This is exterior angle. R will be. So we have I and R's value. See, till here this will be the same. N1 same steps, exact same steps. N1 into I is equal to N2 into R. Same steps. Obviously, because that is your simple Snell's law. Now just put it in here. So N1 will be equal to I. I is gamma minus alpha equal to N2 gamma plus beta. All right. Now again, you will be having tan alpha, which will be approximately equal to alpha. Here, this will also be equal to Mn by No. You will be having tan beta approximately equal to beta. And see, beta will also be here. This will be equal to Mn by Ni. And tan alpha you will get. No, alpha has been considered. What is left? Tan gamma. Gamma is left. So tan gamma will be what? This will be equal to gamma. So above part was Mn by Nc. So now let's keep the value. So this becomes Mn by, it was gamma minus 1, gamma minus I. We had no here when we were dealing with angle of incidence value, that was gamma minus alpha. So this time we'll have it as Mn by Nc minus Mn by No. This is equal to N2. So N2, this becomes the sum you have for gamma plus beta. So Mn by Nc plus Mn by Ni. Fine. So M and Mn gets cancelled everywhere. From all these parts, you have Mn getting cancelled. Right, from all these parts. Now again, Nc can be written as Pc, and No can be written as Po, and which is left, Ni can be written as Pi. Now see, PC will still be minus U. But see, refraction, this radius of curvature, this time radius of curvature is lying where your object is lying. It means if object distance is negative, it is in front of the surface, refracting surface. So we'll take R will also be negative this time. And this will be positive because image is formed on the behind. It is formed behind the mirror. See, this is radius of curvature this time. That was object distance and this is image distance from the pole. This is P pole. Fine, that's why. Any doubts you have, let me know. I can repeat it, though it's already a repetition, but we can do it again. So if we put in the value, this becomes this becomes N2 first. Will come now. Here N2 will come. C class, not N1. Because medium has changed, no? This becomes N1 and N2. C class. If we look here, with the same steps if you do, this is N2. So N2 sin I, N1 sin R. So this is also N2 sin I, N1 sin R. So this becomes N2 by minus R minus N2, U is negative, is equal to N1 by minus R plus N1 by V, just keeping the value. So this becomes N2 by minus R plus N2 by U is equal to N1 by minus R plus N1 by V. Numerical for this, we'll do it in the next class only and we'll start with Lenz's formula. Let's rearrange this also in a little simplified way. N1 by V. So R terms are together, N1 by minus R, and this becomes N2 by R. So from here, if you take the common as -1 negative, you can reverse this, shift it. So you will be left with N2 by minus U plus N1 by V, because we have to shift the formula so that this becomes positive, and N1 minus N2 by R. Again, use the proper convention. So if you have understood the previous part, now you can simply directly quickly note this down, because all the doubts and queries that were present were from the first part. Same, this is exactly the same. It's just that slight differences. That's why I had to write it again. Though again, if you still have any queries from this part as well, you can ask. You're free to ask from there as well. All right, so note it down. If anybody completes it, you can text me done in the chat column and you can leave the meeting. This is for today. One numerical we'll practice on Thursday. You will have a test on Thursday as well as we'll complete with the lens part. Okay. So thank you so much, class. You can text done and you can leave when you are completing.
Thank you, ma'am.
Ma'am, is it supposed to be N2 minus N1 by R?
Where, Krishna?
Ma'am, the last part, because you have taken minus common, right?
Yes, I have taken -1 common from both the parts. No, the second last part includes N2 by N1. Now N2 by U, this is minus N1 by V, and this is equal to N1 by minus R, which is equal to, so see, here if we take common, N1, if N1 is taken common from here, this becomes N2 minus N1, this by U, this is by V, this is equal to minus N1 by R plus N2 by R. You multiply this by -1. So say this becomes N2 by minus U plus N1 by V, right? N2 by, this is minus, I have multiplied it by -1 on both the sides. So minus, this becomes plus, and this becomes plus N1 by R, and this becomes minus N2 by R. Understood? I have multiplied it by -1 on both these sides. Okay, Krishna?
Yes, ma'am.